We've already met the Dirac Delta function a couple of times in this course as examples. So it's good at this point, since what we're going to be discussing next is the Dirac Delta function as a potential, to discuss the general properties of the Dirac Delta function, how it works from the mathematical perspective. What I want you guys to think of when you think of the Dirac Delta function is the limit of a distribution. The Gaussian distribution, for example, rho of x is given by 1 over the square root of 2 pi as a normalization, sigma, e to the minus, say, x squared over 2 sigma squared. The limit as sigma goes to 0 of this function gives you something that is very much like the delta function. This is not the only way to define the delta function, but if we start with, for instance, this purple curve here at large sigma, and this orange curve here at small sigma. As sigma gets smaller and smaller, the distribution gets narrower and narrower and taller. As sigma gets smaller, for instance, the dependence here in the exponent of e to the minus x squared gets faster and faster, since I'm effectively multiplying the x squared by a larger and larger number. And the normalization constant out front, 1 over root 2 pi times sigma, gets larger and larger as sigma gets smaller and smaller. So thinking about this as the limit, in the limit, we have a distribution that is infinitely narrow and infinitely tall. It has absolutely no support for any values of x other than, say, x equals 0 here. So this would be, say, delta of x as a distribution. You often see delta functions written as, in terms of more conventional function notation, delta of x is equal to 0 for x not equal to 0 and infinity for x equals to 0. But this isn't a sufficiently accurate description because it doesn't tell you this property that the delta function is the limit of a distribution. It has specified integral. So you always have to add an extra condition here for something like, for instance, something like the integral from minus infinity to infinity of delta of x dx is equal to 1. That essentially sets the specific value of the infinity here such that the integral equals 1. But thinking of it as the limit of a distribution is essentially the actual definition of the delta function. Knowing that the delta function acts like a distribution allows us to do things like calculate integrals with delta functions. This is where delta functions really shine. If you have an integral of minus infinity to infinity of any function, f of x, multiplied by the delta function, if we think of this as a distribution, this is effectively the expectation of x, of f of x, the expected value of f of x, subject to this distribution given by the delta function. Now, since the delta function has absolutely no support over any values of x other than x equals 0, essentially what this is telling you is the expected value of f of x where the only region that we care about is the area very near 0. So this just gives us f of 0. Thinking about this in the context of a distribution, if we had a distribution with some very narrow width, if this width gets extraordinarily narrow, then no matter what f of x does out here, we don't care. And as the distribution becomes extraordinarily narrow, we're just zeroing in on the behavior of x over this region, which makes f of x basically look like a constant. And you know, the expected value of a constant, like if I wrote this as the expected value of f of 0, it wouldn't matter what the distribution was, it would just give you f of 0. So this is the same sort of concept. The infinitely narrow distribution effectively just pulls out the value of f of x at that point. So this is our first really useful formula with delta functions. If we integrate, it doesn't really matter what we integrate over, minus infinity to infinity will work. Delta of x times any function f of x integrating dx, we just get f of 0. We don't have to do the integral. Delta functions effectively make integrals go away. We can do this not just for the delta function of x, we can do it for delta functions of x minus anything, for instance x minus a. If we plotted this distribution, delta of x minus a, it's going to be 0 except for the point where x equals a. So at x equals a, the argument is delta function goes to 0. So effectively, we've just translated our delta function over by some distance a. It's not the most clear notation. This is the x-axis, and this is a. So what this is going to do, and you can think about doing a change of variables, some sort of u substitution where u equals x minus a, it's just going to give you the value of f at the point where the delta function has support. So this is going to give us f of a. So if we have some way of expressing the delta function, or if we're just using the delta function itself translated, we can pull out the value of f at any point. We can do more with this, though. Instead of just subtracting values in the delta function, we can evaluate the delta function of a function. Again, what we're working with here is integrals multiplied by some other function, since that's how delta functions most often appear in this context. So, if I have coordinates, and what I'm interested in now is g of x plotted as a function of x, suppose g of x looks something like this. I have some places where g of x crosses the x-axis, where g of x equals 0. I know the delta function is going to be 0 for any argument that's non-zero. So essentially what this is going to do is home in on these regions where g of x is equal to 0. And I drew 5 of them here. Doesn't really matter how many there are, but every time as we scan through an x, say calculating this integral, every time g of x goes to 0, we'll have support from the delta function. And it will effectively pull out something related to the value of f of x at that point where g of x goes to 0. Now if you consider a g of x that looks, let me draw a slightly more exaggerated form here. Suppose g of x looked something like this. We have 2 points where g of x crosses 0, but g of x crosses 0 at different rates. Now if I thought of the delta function as the limit of a distribution that's not infinitely narrow but has some finite width to it, I could think about the values, the regions where g of x is between two small values, one slightly positive and one slightly negative. And if you look at some region like this, if I zoom in on this, you have g of x crossing with a steep slope, crossing your axis, and then you have your region between which the delta function of g of x will be non-zero. And if you look at the coordinates here that span that range, you'll get a fairly narrow window. You'll get a much narrower window than if you consider something like the other point here, where g of x crosses the axis, but at a much shallower angle. Now if I'm concerned with that region over which delta function has non-zero value, it's going to be much broader. We're going to be dealing with a much broader range in x than if g of x crosses the x-axis at a more steep angle. Essentially what I'm trying to argue here is the slope of g of x as it passes the x-axis is what determines the effective width of the delta function. Now treating the delta function as a distribution now isn't necessarily as valid, since the overall distribution here isn't necessarily normalized. Delta of x is normalized, delta of g of x is not necessarily normalized. The range over which the delta function has support then will be related to the effective distribution, delta of g of x. For instance here, if g of x crosses at a very shallow angle, the delta function has a broader region of support and therefore is going to effectively pick out a more heavily weighted value of f of x. F of x is still going to act like a constant here. Suppose I have some f of x that I'm multiplying in here, and it looks maybe something like that. F of x is still going to act like a constant, but I'm going to be multiplying the value of f of x at this point by a relatively smaller window than if I'm multiplying the value of f of x at this point. All of this is just a conceptual argument for the form of this function. Delta of g of x is typically written as a sum, and I'll write as a sum over I, of delta of x minus x sub I over the absolute magnitude of the derivative g prime evaluated at x sub I, where these x sub I are the zeros of g of x, the points where g of x crosses the axis. So this would be maybe x sub 1, and this would be x sub 2, in this case if g of x has two zeros. The effective slope of g of x evaluated at the point where g of x crosses the x-axis, where g of x is 0, tells you effectively how things are weighted. That's what I was trying to argue with this slope and the effective width of the delta function at that point. So factoring this out here, writing this factor here in the denominator, g prime of x sub I accounts for that. Steeper slope results in smaller effective window. Larger derivative, steeper slope, results in smaller effective contribution to the overall delta of g of x. To give you an example of how this works, consider delta of ax plus bx squared. I can simplify that a little bit, writing it as delta of ax times times 1 minus b over ax to factor things out. Factoring this makes it very clear that this is going to have zeros at x equals 0 and x equals a over b. If those are our zeros, then this means I have something, let's call this x1 and this x2, that I can use in this formula. So now I need to figure out if this inner quantity here is g of x. What's g prime of x? Well, this is a simple polynomial, so taking the derivative is pretty easy. We get a plus 2bx. Oops, sorry, I've dropped a minus sign here. Let's make that a negative. Let's make that a negative, just for the sake of correctness. The second formula I wrote here was correct. That minus sign didn't just magically appear from nothing. So I know what my x1 and my x2 are. I know what my derivative is. I can evaluate my g prime of x1, and x1 is 0. I evaluate g prime at x equals 0. The second term just drops out, and I get a. I can also evaluate g prime of x2, and if I substitute in a over b for this, I get a over b, and for x here, the b's cancel out, and I'm left with a minus 2a. I get minus a here. So you've got the same effective magnitude of the derivative, which is what's going to be important here. And that should make sense, since the function here, g of x, is just a parabola, looks something like this, between 0 and a. Or sorry, not 0 and a, between 0 and a over b. So substituting in here, we can write this overall, delta of ax minus bx squared is equal to delta of x, where I'm looking at x minus x1, where x1 is 0. So delta of x minus 0 over the absolute magnitude of a, plus delta of x minus a over b divided by the absolute magnitude of minus a, which is just going to be the absolute magnitude of a. So evaluating the delta function of something in an integral context like this allows you to make a transformation to express the delta function as a sum of delta functions delta functions shifted over to where the function that you're evaluating the delta function of, g of x here, equals 0. Keep in mind you're always going to be working with delta functions in this integral context, even when you're working with delta of g of x. So it's not necessarily terribly meaningful to look at this sort of thing, delta function of a function. This sort of transformation is really only going to be useful when you go and substitute it back in when you have some sort of an integral. So let's do another example. Delta function of x cubed minus x times e to the minus x. The g of x we're working with here is x cubed minus x. So I can take the derivative, g prime of x, that's going to be 3x squared minus 1. I can also rewrite g of x as x times x squared minus 1, which I can continue to factor x plus 1, x minus 1. Factoring this is the difference of two squares. So that allows me to re-express my delta of x cubed minus x as, I have 3 zeros from this, x1 equals 0, x2 equals minus 1, and x3 equals 1. So I can express it as a sum of 3 delta functions, delta of x over effective derivative here, which I'll write in a moment, plus delta of x minus 1 over its effective derivative plus, or over the effective derivative of g of x here, plus delta of x plus 1, again over the magnitude of the derivative of g of x. And if you go through and evaluate the magnitudes of the derivatives here, you end up with minus 1 here, 2 here, and 2 here. So this is our overall formula. So what we're going to be integrating then is the integral from minus infinity to infinity of this re-expression of our delta function, delta of x plus delta of x minus 1 over 2 plus delta of x plus 1 over 2, all multiplied by our function e to the minus x dx. Now these are just simple delta functions multiplied by your secondary function. You know these are infinitely narrow normalized distributions now. I've gotten rid of the function inside the delta, re-expressing it just as translated deltas. Which means what you get when you do this integral is just the value of e to the minus x at x equals 0, the value of e to the minus x at x equals minus 1, the value of e to the minus x at x equals minus 1, plus 1 from this one, minus 1 from this one, with these appropriate normalization constants multiplied in. So, evaluating e to the minus x at x equals 0, that's just 1. Evaluating e to the minus x at x equals plus 1, that's just e to the minus x, so I'm adding e to the minus x over 2, from the over 2 here, plus, again, the value of e to the minus x at minus 1, which is just e to the x, over 2. That's our answer. We're done. No actual integration required. To check your understanding here are a couple of integrals for you to do. Translated delta function, simple g of x inside the argument of the delta function, and slightly more complicated but still factorable argument of the delta function. None of these integrals should be difficult. None of them actually requires any integration. This is just to give you a feel for working with the sorts of functions that we'll have to work with in quantum mechanics, for example. You can also take derivatives of delta functions, and the derivative of the delta function is a strange thing to think about. If I have a delta function, thinking about it as the limit of a very narrow distribution, I have sort of a positive derivative on one side and a negative derivative on the other side. So the derivative that I'm going to be working with then, if this is delta of x, and I'll put that in quotes because delta function is of course the limit where it's infinitely narrow and I can no longer meaningfully draw it, the derivative delta prime of x, for instance, which, I don't really like writing it as delta prime. Let's write it as d delta dx as a function of x, is going to be positive, negative, and back to 0. In the limit where the delta function becomes infinitely narrow, these positive and negative excursions are going to become infinitely narrow as well. And you can think, well, it's sort of taking the positive side of a function. If this is going to act like a delta function, it's going to be like x from the function that we're integrating the derivative of the delta function with from the positive side, and then we're going to be, or with a minus sign, we're going to be adding on the value of the function from the negative side. So value from the positive side, value from the negative side, all added up with a minus sign on one and a plus sign on the other. That sort of looks like taking the derivative. And you can see that by looking at this expression and thinking integration by parts. For instance, if I say u, that's going to be f of x, and dv, that's going to be d delta dx dx. I can do integration by parts. My du is going to be df dx times dx, and my v is going to be delta. When I integrate the derivative of the delta function, I'm just going to get the delta function back. So my integration by parts for this expression is then going to tell me my term without any derivatives in it, f of x, delta of x, evaluated the limits of my integral, in this case minus infinity to infinity, minus the integral of the terms with derivatives in them. I'm just going to get delta of x, now integrating again from minus infinity to infinity, delta of x times df dx integral dx. And, well, our boundary term here, f of x times delta of x evaluated at infinity. Well, delta of x, if anything, if x is not 0, delta of x is 0. So this term vanishes. Delta of x not equal to 0 is equal to 0. And what we're left with then is the integral of a delta function times a function, in this case df dx. So it's just going to pull out the value of df dx at x equals 0. So what we're going to get is df dx evaluated at x equals 0. That's our answer. So multiplying f of x by the derivative of the delta function pulls out the derivative of f of x at whatever the argument of the delta function is. You could just as easily have written this as x minus a, the argument of the delta function, and then it would pull out the derivative of f of x at x equals a. This notion of integrals and delta functions pulling out the value of the function gets especially interesting when you talk about delta functions and Fourier transforms. For instance, suppose we're interested in the Fourier transform of the delta function. Capital F of k now represents the k-space representation of f of x, where if this is going to be delta of x, you know how to do this integral. This is just going to be 1 over the square root of 2 pi out front times e to the minus I k, and I've forgotten something. Instead of treating this as just the delta function at specifically x equals 0, I'm going to say x minus x naught. Do things a little bit more generally. So delta of x minus x naught here in this integral is just going to pull out the value of e to the minus I kx at x naught. So this is our Fourier transform of the delta function. It's a function of k, and x naught now is just sort of effectively a constant. In order for this to really make sense, when I take this capital F of k and substitute it back in here, you'll see we need a particular interpretation of integrals of e to the I kx. So let's go ahead and do that. Let's substitute that in. What we're going to get, 1 over square root of 2 pi out front, times another 1 over square root of 2 pi from our capital F of k. So we're just going to have a 1 over 2 pi overall. And we have an integral from minus infinity to infinity of our capital F of k over here, e to the minus I k x naught, times e to the I k x, and we're integrating now dk. So if I re-express this, 1 over 2 pi integral minus infinity to infinity, that's really ugly infinity. I've always had problems with infinities. E to the I, and then I'll write this as k x minus x naught integral dk. So this, as a function of k, x and x naught are constants in this integral since it's an integral over dk. This is just e to the I times something times k. So this is your complex number rotating around in real imaginary space in the complex plane. As k increases, you're just rotating around. So this is effectively a spiral if you want to think about it as a function of k. Depending on the value of k, you're just rotating around. And if I add up, if I think about integrating a function that's spiraling around like that, the real part is going to be a cosine, the imaginary part is going to be a sine, and I'm integrating from minus infinity to infinity. So if you think about the real part as being a cosine, you're integrating a function that just oscillates. And it oscillates all the way to infinity and all the way to minus infinity. So if I say start at 0 and go to infinity, first I'll be adding up some positive, then I'll be adding up some negative, then I'll be adding up some positive, then I'll be adding up some negative. The integral is essentially oscillating as I increase my upper limit. It's also oscillating if I decrease my lower limit. So really you're having an integrand here, or the overall integral, depending on where you stick the endpoints, is oscillating between two values, between positive pi and negative pi, more or less. And it's not really sensible to say that that has any specific value. But keep in mind now what we're trying to get back is delta of x. So really, the only sensible way to treat these integrals is to say that this integral is equal to 0 if x is not equal to x naught. Since that's what the value of the delta function is if x is not equal to x naught here. If x is not equal to x naught, we have this oscillating integrand, and we're saying that when the limit, in the limit as x goes to positive infinity, or the upper limit goes to positive infinity and the lower limit of the integral goes to negative infinity, we end up with 0. That feels a little fishy, but if we make that definition, we get something back that resembles the delta function. If x equals x naught, of course, then the argument here is just 0. We no longer have oscillations, and our function is just constant. And the integral of a constant, the integral of 1 from minus infinity to infinity, had better be infinity if x equals x naught. So this part's okay. The 0 here is a little fishy, but if we make this definition, we get something back that looks very much like what we put in the delta function. So this is how delta functions relate to Fourier transforms, which hopefully sheds a little bit more light on what I was arguing in the lecture on free particle wave packets, being able to, really express anything. So that about sums up what I feel you guys need to understand about delta functions. From minus infinity to infinity of delta of x dx is equal to 1. That essentially sets the specific value of the infinity here, such that the integral equals 1. But thinking of it as the limit of a distribution is essentially the actual definition of the delta function. Knowing that the delta function acts like a distribution allows us to do things like calculate integrals with delta functions. This is where delta functions really shine. If you have an integral of minus infinity to infinity of any function, f of x, multiplied by the delta function, squared over 2 sigma squared, the limit as sigma goes to 0 of this function gives you something that is very much like the delta function. This is not the only way to define the delta function, but if we start with, for instance, this purple curve here at large sigma, and this orange curve here at small sigma, as sigma gets smaller and smaller, the distribution gets narrower and narrower and taller. As sigma gets smaller, for instance, we've already met the Dirac Delta function a couple of times in this course as examples. So it's good at this point, since what we're going to be discussing next is the Dirac Delta function as a potential, to discuss the general properties of the Dirac Delta function, how it works from the mathematical perspective. What I want you guys to think of when you think of the Dirac Delta function is the limit of a distribution. The Gaussian distribution, for example, rho of x is given by 1 over the square root of 2 pi as a normalization, sigma, e to the minus, say, x squared. The dependence here in the exponent of e to the minus x squared gets faster and faster since I'm effectively multiplying the x squared by a larger and larger number. And the normalization constant out front, 1 over root 2 pi times sigma, gets larger and larger as sigma gets smaller and smaller. So thinking about this as the limit, in the limit, we have a distribution that is infinitely narrow and infinitely tall. It has absolutely no support for any values of x other than, say, x equals 0 here. So this would be, say, delta of x as a distribution. You often see delta functions written as, in terms of more conventional function notation, delta of x is equal to 0 for x not equal to 0, and infinity for x equals to 0. But this isn't a sufficiently accurate description because it doesn't tell you this property that the delta function is the limit of a distribution. It has specified integral. So you always have to add an extra condition here for something like, for instance, something like the integral from